So this one is June 2016 paper, Unit 6. I'll discuss some questions from this paper. A series of tests is carried out on aqueous solution X, Y, and Z. Each solution contains a compound of different D block element. So all of them contain a D block element. Test A and B described in table are carried out on solution. 1 cm cube of solution X in a test tube, we add sodium hydroxide until no further change. White precipitate dissolve in excess. And then we add aqueous ammonia and give white precipitate dissolve in excess. So what this, write a formula for the precipitate. So what this gives an idea, because if precipitate, first it was white PPT, white precipitate, and then dissolve, and then white precipitate with aqueous ammonia, and then also the precipitate dissolve. So what this gives an idea, this gives an indication that zinc ion is present or Zn is present. So what will be the formula of a complex ion? So they are asking that is present at the end. If it was in between, because precipitate is there, so it will be a hydroxide. But because it is, so when zinc existing, like example, you have a solution, aqueous solution which contain a zinc ion. So zinc is +2, but how it exists? It exists as a complex. So the charge on the complex will be +2. But when we add sodium hydroxide, so we have zinc hydroxide, like zinc complex is there. When we add sodium hydroxide or NaOH or aqueous ammonia, there is an acid-base reaction like the two hydroxide ions will accept protons. So as a result, it will turn into zinc hydroxide plus four extra water molecules are there. So this will be a formula for complex. But that is a formula for precipitate. But when we add further, so because zinc is amphoteric, zinc hydroxide is amphoteric, means it can further react with alkali. So as a result, what will happen? More protons will be lost. And what will be the formula of a compound? So it will be zinc. It will lose further 2 more protons. So it will become ZnOH4 and H2O will be there too. So this is a formula of the complex. So +2 and this will be -4. So overall charge will be -2. Is it clear how we work out the formula of a complex ion? Then write a formula for complex ion that is present at the end of test B. So which one is present at the end of, look, for with sodium hydroxide, why the precipitate dissolve? Because it was the amphoteric nature first when we had acid-base reaction, and then hydroxide is also amphoteric, so as acid-base reaction. But why the precipitate dissolve with aqueous ammonia? Because there is a ligand exchange. So when you was having a complex, a zinc is present in the aqueous solution. It contains 6 water molecules. But when we add aqueous ammonia, first reaction is acid-base reaction. Ammonia is a proton acceptor, so it will accept proton. It will become zinc, OH2 and H2O4 plus NH4 will be there. So this is a precipitate. But then when we add further, the precipitate dissolve. So more ammonia is added. As a result, when more ammonia is added, why the precipitate dissolve? That is a ligand exchange, like these OH and water molecules are replaced by ammonia molecule. So you can write Zn, NH3 is there, 4 of them, or H2, any number you can mention, but the total should be 6 for a ligand, and overall charge is, ammonia is a neutral ligand, water is a neutral ligand, but zinc is +2, so overall charge will be 2 plus or +2. So the first one, the precipitate dissolved due to acid-base reaction and the amphoteric nature of the zinc. And the second one, the precipitate dissolved to form a colorless solution, is due to a ligand exchange. First, there is an acid-base reaction, and then there is a ligand exchange. Test D described in table is carried out on solution Y. So there is another solution because we have X, Y, and Z. So 2 cm cube of solution Y in a boiling tube, and we add dilute sodium hydroxide. So when we add sodium hydroxide drop by drop, like small drops of sodium hydroxide are added. First, it gives a green PPT, and green PPT dissolved to form a green solution. So what this gives an idea? This gives an idea because if it was iron 2, then it will be green precipitate, which should be insoluble. But because it dissolves, it gives an idea there is a chromium plus 3 ion is there. We add sodium hydroxide and hydrogen peroxide. Hydrogen peroxide is basically an oxidizing agent. It will convert this chromium plus 3 to chromium plus 6. And there are two compounds which can exist like chromium plus 6 is there. One is a chromate, CrO4. One is a CrO4 and another one is a dichromate, Cr2O7. Both compounds, the chromium is plus 6. But they can exist depending on the nature of solution. So we add sodium hydroxide. The purpose of the sodium hydroxide, because in alkaline or acidic condition, we will have different types of chromate. So when we add hydrogen peroxide is an oxidizing agent. As a result, when it is an oxidizing agent, it will produce chromium plus 3 to chromium plus 6, and that chromium plus 6 can be existing as a dichromate or chromate ion. Write an ionic equation which includes state symbols for formation of the precipitate. The precipitates, because we add sodium hydroxide, so the precipitates, remember, are always hydroxides. So what happened? We want basically it formed chromium 3 hydroxide, CrO. So what ions are present? So it contains a chromium plus 3 ion and it contains 3 hydroxide ions. So chromium plus 3 and 3 hydroxide as a result will produce chromium hydroxide. Then give the oxidation number before adding hydrogen peroxide. So before adding hydrogen peroxide, it was plus 3, but after it will become plus 6. The reason is hydrogen peroxide is an oxidizing agent, so it converts chromium plus 3 to plus 6. Then test D described in the table. Test D is described in the table carried out on a solution Z. 2 cm cube of solution Z in the test tube. We add equal volume of a dilute sodium hydroxide. First, what happened? Off-white precipitate. Off-white precipitate which darken. So basically, off-white precipitate are due to Mn plus 2. So remember, the off-white precipitate are due to Mn plus 2. So give a formula for D block metal or cation present in solution Z. So which D block cation is present? So it contains Mn plus 2. So this is related to memorizing the color of the precipitate. Another question, ethyl ethanoate is hydrolyzed in the presence of the catalyst. Hydrochloric acid is there. Different values are given. Show that 25 cm cube of equilibrium mixture contains 0.096 moles of ethanoic acid. So how we can work out, as you can see, In this reaction, we were having a 15 cm cube of and 0.153 mole of ethyl ethanoate, 10 cm cube of hydrochloric acid of concentration 1 mole per dm cube mixed together. And in this pre-equilibrium, like before equilibrium, 0.556 moles of water are already there. It is left. Then using a pipette, 5 cm cube of a sample was taken from 25 cm cube equilibrium mixture, and this 5 cm cube is titrated with sodium hydroxide. So this sodium hydroxide or NaOH will react with what? Because we take out a 5 cm cube sample. So this will contain all. It will contain ethyl ethanoate, it contains water, it will contain alcohol, and it also contain ethanoic acid. But sodium hydroxide will only react with ethanoic acid. Why it will react with ethanoic acid? Because there's an acid-base reaction. So using the volume of sodium hydroxide and the concentration of a sodium hydroxide, first we'll find the moles of sodium hydroxide. Then using the equation, after getting a moles of sodium hydroxide, we'll find the moles of ethanoic acid. And from moles of ethanoic acid, that is the moles in 5 cm cube, because what we did, we were having a reaction mixture which is 25 cm cube, but out of 25 cm cube we only take out 5 cm cube. We did not remove all, we just take out. So if we will get the mole, and that was titrated, so we'll find the moles of acid in 5 cm cube, and in 25 cm cube it will be 5 times, because comparative volume is 5 times, so it will be 5 times the number of the moles which are present in 5 cm cube. So concentration into volume, first we'll get the moles of sodium hydroxide. This concentration into volume will give us the moles. So concentration is 0.5 and the volume is 42.4 divided by 1000. This will give us the moles of what? Sodium hydroxide, which will be 0.021. These are the moles of sodium hydroxide. Then we will use a ratio between the sodium hydroxide and ethanoic acid. The ratio between them, when you write a balance equation, it is 1:1. So if we have 0.021 moles, this will be X moles of ethanoic acid. We'll get the same answer, which is 0.021. But that 0.021 is in 5 cm cube. We want in 25 cm cube. So the volume is twice, so the moles will also become twice, which are 0.106. So these are the moles. And now in the question, as we mentioned already, that in this pre-equilibrium, like before the equilibrium was reached, we were having 0.556 moles and we were having 0.153 moles of ethyl ethanoate. And so first, because we have to show 25 things, it contains 0.096. So we have to show that this answer is 0.096. So how we can show? This is the number of the moles which we have calculated in 25 cm cube. And now original, when you check, as I mentioned here in this part, the amount of a hydrochloric acid, because what happened, ethyl ethanoate and hydrochloric acid will react with each other. So when they will react with each other, as a result, they will give moles of ethanoic. So, or the reverse reaction, because the reactants can form a product can form back the reactant. And in a pre-equilibrium, we were having a 10 cm cube and 1 mole per dm cube hydrochloric acid. So these are the total number of the moles, because we already have HCl. See, we have HCl in the mixture and we have ethanoic acid also in the mixture. And the total number of moles of acid, because this is basically giving the total number of moles of acid, which are 0.106. That is the total number of moles of hydrochloric acid and ethanoic. So we'll find the moles of hydrochloric acid concentration into volume. So concentration in 1 and the volume is 10 divided by 1000. So it will be 0.01. So if the total number of moles of acid are 0.106 and moles of HCl which are already there is 0.01, so how many moles of ethanoic acid? So it will be 0.106 minus 0.01. So this will give us the total number of moles, which is about 0.096 moles. So the sodium hydroxide is actually reacting with both hydrochloric acid and ethanoic acid. So we get the total number of moles, and total number of moles minus the moles of HCl will get how many moles of ethanoic acid are there in the mixture. Then the next part, we have to deduce the number of moles of each of the other components in equilibrium. So for this, we have to first write the equation that the ethyl ethanoate C2H5COO CH3, because ethyl ethanoate is there. So CH3COO C2H5 plus H2O gives CH3CO ethanoic acid and ethanol. C2H5 will be there. So we already worked out the moles of ethanoic acid at equilibrium, which were 0.096. So this was 0.096 at equilibrium. And remember, how many initial moles were there? Like in the beginning, the number of the moles of water were given initially 0.556. The number of moles of ethyl ethanoate were initially given 0.153. This was 0 and this was also 0. But at equilibrium, we already calculated at equilibrium. This one is 0.096. Because the ratio between ethyl ethanoate and ethanol is 1:1, so same number of moles of ethanol will be produced, so 0.096. And how many moles of water will be there? So it will be 0.556 minus 0.096, so remaining moles will be the 0.46. And number of moles of ethyl ethanoate 0.153 minus 0.096, because 1:1 is the ratio. So if 0.096 moles of ethanoic acid is produced, same number of moles of ester will be used up. So we are not finding how many used up, we are finding how many are left at equilibrium. So the number of moles which are left, 0.153 minus 0.096, that is equals to 0.057. So these are the moles of these reagents, reactant and product at equilibrium. And using the moles, give the expression for Kc. Kc is a product divided by reactant, and this is a homogeneous equilibrium. Homogeneous means they all have the same states. So the Kc is a product. So C2H5OH, CH3COOH, CH3COO, C2H5 and H2O. So product divided by reactant will give us the expression for Kc. Now we just have to substitute the values which we have calculated in the previous and get them. But we normally substitute the concentration here, but we can substitute the moles. Why we can substitute the moles? As you can see, there will be no unit for this Kc because concentration is mole per dm cube, mole per dm cube, mole per dm cube, and mole per dm cube. So These all d and q will cancel with each other, moles will cancel, so it does not make difference. If we substitute the moles or the concentration, we will get the same result or same answer. So even we can substitute the moles at equilibrium and we'll get the right answer. Then explain why it is possible in this case to calculate Kc using the moles rather than concentration. So same thing as I mentioned, because Kc is not having any unit, so we can use the moles rather than concentration. Then the experiment was repeated by student whose Kc differed from A4. The student made several suggestions. State and explain how it will affect the value of a Kc. Student suggested one, that concentration of a sodium hydroxide used by the solution is less than 0.5. So if a student use a small concentration, means he will need a large volume. And if he need a large volume, so he will get the greater concentration of sodium hydroxide. So because if concentration, he will get the greater moles of sodium hydroxide. Concentration is less, so for a complete reaction, he need more volume. So the product, because if you use a large volume, so the number of the moles likely to come out more, even though a smaller concentration but large volume comparatively. So the number of moles which will come out with a calculation will be higher. And if the number of moles are higher for sodium hydroxide, the number of moles of acid, ethanoic acid, and hydrochloric acid, that will also come out more. And if the number of moles of acid are more, as you can see, acid is a product here, the ethanoic acid. So if we have more product, it means the value of the Kc will increase. So this is the ethanoic acid. It will have a higher value of Kc. And then suggestion 2, a mixture has been left in a warm place and the equilibrium has been reached at a temperature above the room temperature. So if we leave the mixture at a warm place, what will happen? There will be more dissociation, because the ethanoic acid will, like ester, will dissociate more. As a result, when greater dissociation, more product, it means the value of the Kc will also increase. Then a second student repeated the original experiment using the same method. However, using a pipette and a burette were taken from a top meniscus. How it will affect the volume of equilibrium mixture delivered from the pipette. So if we use a top meniscus, because normally when we read the bottom of the meniscus. So if a student read the top meniscus and like using a pipette. So this example, this is a 25 marks, but he read the, so this is a 25 marks. And if student read the top meniscus, so if a student read the top meniscus, the bottom of the meniscus, because normally we should use that bottom of meniscus, but student read the top meniscus. So means the actual volume which is transferred will be smaller. So if the actual volume, as how it will affect the volume of equilibrium mixture delivered from the pipette, so the volume of the equilibrium mixture will be smaller, because for a complete 25 cm cube, how it should appear. So for a complete 25 cm cube, lower meniscus we will read. So this will be 25. So if the level is lower, like student read in this manner. So this will deliver a smaller volume in the flask as compared to when we read the lower of the meniscus. And how it, if at all, this affects the volume of sodium hydroxide. So how it will affect the volume of a sodium hydroxide used? So if we need a, because if less acid molecules are there, so less sodium hydroxide is needed, so the volume of sodium hydroxide will decrease. Because sodium hydroxide is reacting with the acid. If we are using a smaller amount of acid, it means we need less amount of sodium hydroxide. One of the student titer was 42.6. We have to calculate the percentage uncertainty. Percentage uncertainty is equals to uncertainty, the smallest value which instrument can record, divided by value recorded into 100. So the percentage uncertainty is a uncertainty. So uncertainty is 0.05. But because when we are using, if a apparatus is used twice, how we use a burette? First we read, when we are using a burette, first we read the first volume, like initial volume, and then we read the final volume and we take the difference. So burette reading is always like measuring the first volume, that is V1, then measuring the second volume, that is V2, and the difference in the volume will give us the burette reading. So it should be twice 0.05 multiplied by 2 divided by value recorded, which is 42.6 into 100. So this will give us the percentage uncertainty. So remember, when we are using the apparatus twice, if it was a pipette, then we will not multiply by 2, because pipette we only use once. Like we just fill the pipette and that's the full volume. So it will come out as 0.23%. So these are first two questions from June 16 paper. Next session we'll do more papers from this, like more questions from this paper.